Hello everyone, welcome to my YouTube channel. This is Enoch's Tutorials. In this video, we are going to look at a full lecture on carbohydrates. Don't forget to like, subscribe, and press the notification bell after watching so you can receive every bit of update from this channel. So, what is carbohydrates? So, by definition, we say carbohydrates contains three main elements. So, the three main elemental composition of carbohydrates is carbon, hydrogen, and oxygen. So, from the word carbohydrate, it means that carbohydrate compound is made of hydrate of carbon. So a carbon element with several water molecules, so to say carbohydrates, from the word carbo and hydrate. The hydrate means that it is water which is made of hydrogen and hydroxy group. Carbohydrates having a general formula of CxH2OY. So this one represents the general formula of all carbohydrates. Every carbohydrate has a carbonyl functional group and several hydroxy groups. So we define carbohydrates as polyhydroxyaldehydes or ketones because it has a hydroxy group that surrounds either an aldehyde group or a ketone group. Or we can also say carbohydrates is a compound that yields a polyhydroxyaldehyde or ketone on hydrolysis. So we define it as a polyhydroxyaldehyde or a polyhydroxyketone, or a compound that yields either a polyhydroxyaldehyde or ketone upon hydrolysis. So an example of a carbohydrate, we know the common ones are what we call glucose. So glucose, we say it is made of carbons, which are several hydroxy groups. So each of these carbons is hydrated. So you see carbohydrate is a hydrate of carbon. It's a hydrate of carbon. The same thing applies to fructose. This one has an aldehyde group. This one has a ketone group. So each of these ones has either an oxygen or OH attached to it. So you see carbohydrate is a hydrate of carbon, which means each of the carbon elements is hydrated. It has several hydroxy group and hydrogen group, which can form water or hydrates around it. So let's say we have this compound glycogen in the body. So glycogen is a carbohydrate because it is a compound that upon hydrolysis by let's say an alpha amylase, it gives a polyhydroxyaldehyde, which is a glucose. So we see carbohydrate is a compound that upon hydrolysis can give a polyhydroxyaldehyde or ketone. Or we say carbohydrate is a hydrate of carbon because the carbon element in the carbohydrate is hydrated, made of several hydroxy groups and hydrogens. Carbohydrates serve several functions in the body. The known ones are for energy production. It serves as intermediate of metabolism. It is a form of storage of energy in the body or even in plant. So carbohydrate is stored as starch in plant and glycogen in animals. It forms structural component of some cells like cellulose, which form the cell component of plant cell. They can be used for fibers, or they have a sort of fibers which helps in prevention of constipation in the body, or also the constituent of nucleotides. Nucleotides like ribose, which form constituent components of nucleic acid like RNA and DNA. Some carbohydrates can also be used for detoxification in the body. So these are the key functions of carbohydrates in the body. Now let's come to classification schemes of carbohydrates. We can classify carbohydrates based on several parameters. So about 4 known parameters are based on to classify carbohydrates. First, we can classify carbohydrates based on the size or based on the size of the carbon chain. So we have the first one based on the size of the carbon chain. We have the second one based on the number of sugar units or the number of monosaccharides or the number of monomer units. Based on the location of the carbonyl functional group, or based on whether it is an aldehyde or a ketone, and also based on what we call stereochemistry. So we have 4 main parameters which we base on to classify carbohydrates. So based on the size of the molecule or based on the size of the sugar units, we have about 3 or some books say 4 categories of carbohydrates. So you can have what we call monosaccharides, you can have disaccharides, you can have oligosaccharides and polysaccharides. So the monosaccharides is just what we call simple sugars. They are simple sugars whose carbon atom ranges from about 3 to let's say 6. Example is what we call glucose, fructose, and galactose. So these are all examples of monosaccharides. Some books place the disaccharides under oligosaccharides and say we have three. So we have monosaccharides, oligosaccharides, and polysaccharides. They are all correct. So with a disaccharide, you can have a lactose, which is made of glucose and galactose. You can have sucrose, which is made of glucose and fructose, and maltose, which is made of two glucose monomers or units. Some other complex carbohydrates include oligosaccharides, which is made of more of the monosaccharide units. For example, if you have oligosaccharide which has about 3, one which has about let's say 4, 5 and above, then we see they are complex carbohydrates. A well-known polysaccharides in the body are what we call starch, which is a form of energy storage in plants, glycogen in animals, and cellulose, which form the cell component of plant cell. So now let's look at carbohydrates. The first one, which is called the monosaccharides. So the monosaccharides, we say they are known as simple sugars. As we give examples above, we have glucose, galactose, fructose, and many other simple sugars. We can also classify monosaccharides in several ways. We can classify monosaccharides based on functional groups, based on carbon numbers, based on some distinguishing groups. For example, if you have a functional group category like aldose or ketose, an aldose sugar, or let's say monosaccharide, is a monosaccharide which contains an aldehyde functional group. Let's say an aldose sugar is a sugar which contains an aldehyde functional group. We're going to have examples in the next slide. Or say ketose sugar is the one who has a ketone group. So we have an aldose from the word aldehyde and ketose from the word ketone. So the aldose is the one with an aldehyde functional group, and also ketose, the one with a ketone functional group. The next one is the number of carbon numbers. So we can have a carbohydrate with 3 carbons, which you call trioses, that with 4, which you call tetroses, that with 5, which you call pentoses, that with 6, which you call hexoses. You can even get 7, which you call heptoses. Now you can also blend these two functional groups and it's to call a sugar. So let's say if a sugar is made of an aldehyde functional group and is made of 5 carbons, we call it an aldopentose. If let's say it is made of a keto functional group and made of 6 carbons, we call it a ketohexose. For example, you have let's say an aldehyde functional group and let's say 3 carbons, you can say an aldotriose. If you have let's say a ketone functional group and it's made of 4 carbons, you can say a ketotetrose. Roughly, if you have let's say an aldehyde functional group with 6 carbons, we can say an aldoheptose. So this is functional group and carbon number blend together. Then we can also have groupings based on some distinguishing groups. So some groupings are very distinguishing. We can have a deoxy sugars, those without one of the oxygen. So here, deoxy sugars are sugars that has lost one of the oxygens. A typical example is the one found in nucleic acid DNA. DNA has a lost OH on the carbon 2. So DNA is a deoxyribose sugar. We have an amino sugars in which one of the hydroxys has been bonded to an amino group. You can have a sugar alcohol in which the sugar has been bonded to form with an alcohol called glycosides, and also sugar acids in which the sugar has been oxidized to form what we call an acid. You can have a ring form of a sugar where you have a furanose and a pyranose. So a furanose is a 5-membered ring in which one of the atoms in the ring is an oxygen, and a pyranose is a 6-membered ring in which the one of the atoms in the ring is an oxygen. So take note, you're going to have examples of how all these ones look like in some few more slides. Okay. So let's continue. So these are some few extra terms that we are to define. So some additional terms to what we discussed so far. We have an aldose, which is a carbohydrate that contains an aldehyde group. A ketose, which is a carbohydrate that contains a ketone group. A triose, let's say a carbohydrate having 3 carbons. A tetrose, a carbohydrate having 4 carbons. An aldopentose, that is a 5-carbon carbohydrate that contains an aldehyde group. And a ketohexose, a 6-membered carbohydrate or 6-carbon carbohydrate that contains a ketone group. So this is just a summary of the whole classification scheme. We have here the summary of the whole classification scheme. So we have the 3 main categories of carbohydrates based on the number of monomer units. We can have monosaccharides, oligosaccharides, and polysaccharides. So from the monosaccharide, we can functional group categories, that is aldoses and ketoses. Examples are fructoses and glucose. Based on the number of carbon atoms, you can have trioses, tetroses, pentoses, hexoses, and heptoses. So this one is 3 carbons, you have 4 carbons, 5 carbons, 6 carbons, and 7 carbons. We can have disaccharides which falls under oligosaccharides. So we have maltose, lactose, and sucrose. These are examples of oligosaccharides, that is disaccharides. We can have trisaccharides, which is made of 3 monosaccharides. We have raffinose as an example. Then we have a tetrasaccharide, which is made of 4 carbons. You have stachys as an example. Now when we come to polysaccharides or complex sugars, we have 2 main categories of polysaccharides. We have the homopolysaccharides and heteropolysaccharides. The homopolysaccharides are made of 1 and only 1 monomer unit. You can have starch, dextrins, glycogen, cellulose, and inulin. So all these sugars are what we call homopolysaccharides because they are just made of 1 and only 1 monomer unit. The next one is heteropolysaccharides. As the name implies, it is hetero because it's made of several or more than 1 monomer unit. You can have the uronic acid, you can have heparin, chondroitin sulfate, you have dermatan sulfate, and keratin sulfate. All these ones are made of different monomer units, so we say they are heteropolysaccharides. So we have 2 main categories of groupings of polysaccharides. We have homopolysaccharides, which is made of just 1 and only 1 monomer unit, and also a heteropolysaccharide. So taking monosaccharides as a unit, we can have an aldose, which is made of an aldehyde group like glucose. So here, this is how glucose look like. It has several hydroxy groups around each of the carbons and an aldehyde group. This explains why we say glucose is an aldose. It is an aldose because it is made of an aldehyde group. Another one is what we call fructose, which is made of a ketone functional group. So ketose or fructose is an example of a ketose because it contains a ketone functional group. And each of these carbons are surrounded by hydroxy groups and hydrogen. That's why we say carbohydrate is a hydrate of carbons. So don't forget to distinguish have a distinguishing feature between ketoses and aldoses. One is made of just aldehyde, one is made of just ketose. So based on the number of carbons in an atom, as we discussed earlier, you can have this sugar, which is made of 3 carbons, which is called a glyceride. You can have this sugar, which is made of 4 carbons. So this one is a triose. This one is a tetrose, which is called a retrose, made of 4 carbons. You can have a pentose like ribose, made of 5 carbons, and a hexose shown here. This one is made of 6 carbons. So each of these can either be an aldose or a ketose. You can have a ketose with 3 carbons, a ketose with 4 carbons, a ketose with 5 carbons, and a ketose with 6 carbons. You can have, let's say, dihydroxyacetone as a triose. You can have erythrulose as tetrose. You can have, let's say, ribulose as a pentose, and also a fructose as a hexose. So it can have both aldehyde and a ketone functional group in it. So these are some common known examples of monosaccharides. So you can have glyceride, you can have glucose, you can have fructose, galactose, and ribose. So these are their respective functions or respective roles they play. So the ribose is the main component of RNA. Galactose is part of milk sugar. Fructose is used as a sweetener. The glucose is present in most of our diet. Then glyceride is just a simple sugar. So most naturally occurring carbohydrates are D and enantiomers. This signifies the structure only, not the direction of the optical rotation. You're going to have look at the meaning of what you call enantiomers and also discuss what is meant by optical rotation or optical activity in the next few slides. So we say all carbohydrates are having chiral centers. Every carbohydrate has a chiral center because it has several groups around it. Now a chiral center is a center within a molecule that has 4 different groups around it. So let's take this carbon here. This carbon has this methyl hydroxy methyl. It has the formal, it has hydrogen and a hydroxide. So this we say this center is a chiral center. So a chiral center is a center which is bonded to 4 different groups. So we have 4 different groups bonded to the center. So you can say this center is a chiral center. The next one here is the enantiomeric component of this. So enantiomers are basically compounds that are having different arrangement of hydroxy and hydrogen on a carbon. So or on a carbon, and they are also mirror images. So mirror images of one atom or one compound is its enantiomeric form. So with here you can see that the OH is at the left, with here see the OH at the right. If you place a mirror here, what you are going to see in the mirror is this. So if you place a mirror here, the image of this that appears in the mirror is this. So we see these two compounds are enantiomers. They have a chiral center that enables the rotation. So this center is called a chiral center or chiral carbon that enables the rotation of the hydroxy and hydrogen around it. So glyceride is a typical example of a chiral compound. So it has one chiral carbon that is marked with asterisk above. So that is this carbon is the chiral carbon. It is chiral because it's bonded to different groups. The chiral compound or center also enable what you call an optical rotation. That is when you pass a plane polarized light through a compound. Compounds with a chiral center and having no point line of symmetry rotate the light or rotate the light ray or the plane polarized light either to the left direction, which we call the lever rotation, or to the right, which we call the dextro rotation. Some other carbohydrates can have more than one chiral center as shown here. One like glucose is having 1, 2, 3, and 4 chiral centers. Unlike that of glyceride, which has only 1 chiral center. Some carbohydrates can have more than 1 chiral center. So you can have 1, can have 2, can have 3, and 4. So if you have, let's say, a ribose, you will have chiral centers. If you have, let's say, a pentose, for instance, it will have 5 chiral centers only if it is an aldose. The chiral centers is a point of rotation that is found in a sugar, and because of the differences in positioning of the compounds or atoms around the chiral center, one carbon can exist in several isomeric forms. So chiral centers enable compounds to rotate plane polarized light that passes through them. Now let's study what is called stereochemistry. So in the basic sense, when we have a compound, two compounds with the same molecular formula but different structural formulas, we call that compounds isomers. So we call them isomers. Isomers can be differences in functional groups or differences in how atoms are bonded in space. So we say we have two main types of isomers. We have what is called constitutional isomers, which is based on just the differences in the bonded system in the compound or the differences in functional group in the compound, and also what we call the stereoisomers. So the stereoisomers is the one we are going to study under the field of chemistry called stereochemistry. And this one just depicts how the atoms are bonded in space around a central atom. So when you have a sugar molecule, each of the chiral carbons might have or can have different positioning of the H and the OH. So with here you can see the H is at the left position, here the H is at the right, at the right position here, and is at the left position here. So you see these two sugars are what we call stereoisomers because they differ in the bonding system of the groups around the chiral center in space. So the stereoisomers, they have the same chemical formula but differ in the position of hydroxy groups on one or more of their asymmetric carbon. So we call the chiral carbons also asymmetric carbon. Bear in mind, chiral carbons or chiral centers are also called asymmetric centers or asymmetric carbon. A sugar with an asymmetric centers usually has 2 to the power n stereoisomers. So as we said earlier, unless it has a plane of symmetry. If you have a sugar with, let's say, more than one chiral centers, it can exist in several isomeric forms. That is, can have different arrangement of the hydrogen and hydroxy on the chiral carbons. So for you to determine the number of possible isomers from a sugar, the formula here is 2 to the power n. So this n is to the power, where n represents the number of chiral centers. For example, if you have, let's say, a glucose like this, the number of possible isomers that this glucose can have based on the different arrangement of the hydroxy group and hydrogen on this glucose is given by the formula 2 to the power n, where n represents the number of chiral centers. So here you can have 1, 2, 3, and 4 chiral centers. So we have 1, 2, 3, and 4 chiral centers. So 4 chiral centers means that the number of isomers present in the sugar glucose is 2 to the power 4, which gives us 16 different isomers of glucose. Another one, galactose too has 1, 2, 3, 4. So the number of isomers in galactose is about 2 to the power 4, which is 16. If you take a sugar like, let's say, ribose, which has about 3 chiral centers, the number of possible isomers is given by 2 to the power 3, which is 8 different isomers. So we have several examples of enantiomers, or sorry, stereoisomers. We can have what we call enantiomers, the one that we discussed earlier. So enantiomers, we say they are sugars that are mirror images of each other, but they are not superimposable. So enantiomers are sugars that are mirror images of each other, but they are not superimposable. They are mostly represented by D and L. D and L. So the D just depict the fact that it is, or the hydroxy on the last chiral carbon is at the position, or at the right position. And the L shows that the hydroxy on the last chiral carbon is at position, or is at the left position. So this is why we say it is a D-glucose, because the hydroxy on the last chiral carbon, which is the carbon 5, it is at the right position. And here it says D-galactose because the hydroxy on the last chiral carbon is at the right position. So enantiomers are basically sugars that are mirror images of each other, but they are not superimposable. So if I place a mirror here, what I'm going to see in the mirror is the image of this. So D-glyceraldehyde and L-glyceraldehyde are examples of enantiomers. The next one is diastereomers that are not mirror images of each other. So some sugars like ribose and xylose, they may have opposite configuration, alright, but maybe they will have different spatial arrangement of the hydroxy groups. So they may have opposite configuration, but they are not mirror images. These are what we call diastereomers. The next one is what we call epimers. So epimers are very simple. When two sugars differ in position of the hydroxy and the hydrogen on one and only one carbon, we say those two sugars are epimers. So galactose and glucose are examples of epimers because they differ in position of hydroxy group on position 4 only. So just position 4 only where they differ. So galactose and glucose are example of epimers. So for example, D-glucose and D-galactose are epimers that differ at carbon 4. Let's look at this one too. This is glucose, and this is mannose. So you can see that glucose and mannose only differ at position 2. So glucose and mannose are epimers at position 2. Then glucose and galactose are epimers at position 4 because they only differ in the configuration of the OH and H at position 4, whereas glucose and mannose differ in position of OH and H at position 2. So take note, when we are being asked to give an example of epimers, you can say glucose and mannose at position 2 or glucose and galactose at position 4. So these are some known examples of D family of sugars. When we say D family of sugars, then we say they are sugars whose OH on the last chiral carbon is at the right side. So if you take this one, for instance, this is a D sugar, which is a triose. This one is a D sugar, a tetrose, a tetrose. We have a D sugar, which is a pentose. So these are all pentoses. They also have D sugars that are what? Hexoses. So they are all D sugars because they are OH on the last chiral carbon, which is the carbon 5 if it is a hexose, carbon 4 if it is a pentose, carbon 3 if it is an what do you call it? A tetrose, and carbon 2 if it is a triose. They are found at the right position. So as seen here, in the D family of sugar, the OH group on the stereocenter, so the stereocenter, another word for what do you call it? Chiral centers. Stereocenter, a symmetric center, or chiral center, are the farthest from the carbonyl is on the right of the fixture projection. So this way of drawing sugars are what they call the fixture projection form of the sugar. So if it is like this, just a straight chain like this, we call it a fixture projection. Sometimes it can be circular if it finds itself in an aqueous solution. That one is called the Haworth projection form of the sugar. Let's look at some kind of reactions that sugars undergo, what they call hemiacetal and hemiketal. In the basic sense, if I have an aldehyde group, and I add an alcohol, if I have an aldehyde group and I add an alcohol to it, there's going to be a possible reaction. If I have an aldehyde and I add an alcohol, I'm going to form what we call a hemiacetal. If I have a ketone and I add an alcohol, I'm going to form what we call a hemiketal. So here is an aldehyde and this is an alcohol. The reaction produces what we call a hemiacetal. So the first thing is this carbon bonds to this oxygen. Then this oxygen abstracts this hydrogen. So we have a hemiacetal. If I have a ketone and I add an alcohol to, I'm going to form what we call a hemiketal. A hemiketal. So the difference between a hemiketal and hemiacetal is that for the hemiacetal, the core carbon, the central carbon, is bonded to one and only one carbon. For hemiketal, the central carbon is bonded to two different carbons. So these reactions are also undertaken by what we call sugars. When sugars find themselves in an aqueous solution, they form what we call cyclization. You have this sugar as a linear form. Let's say this is a glucose. Mostly, the OH on the last chiral carbon, it is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. The OH on the last chiral carbon serves as an alcohol and forms a hemiacetal linkage with the carbonyl carbon. This is the carbon 1. So here, the OH on the carbon 5 of the glucose bonds to this carbon to form what we call a hemiacetal form. If it is a hemiketal, like the case of fructose, the OH here on carbon 5 bonds to the carbonyl on carbon 2 to form a hemiketal. So this is a hemiacetal because it's a reaction between an aldehyde group and an alcohol, and this is a hemiketal because it is between an aldehyde group, ketone group and an alcohol. So this is just a brief written. You say monosaccharides have OH and carbonyl groups on the same molecule as shown because they are called polyhydroxyaldehydes, ketones, and exist almost entirely as 5 and 6 membered rings. So as we discussed earlier, the 5 membered ring is what we call a furanose or a furan, and the 6 membered ring is what we call a pyranose or a pyran. When the cyclization occurs, the compound that is bearing, or the carbon bearing what they call the functional group, in the case of aldehyde or ketones, that carbon is called an anomeric carbon. So after cyclization, the anomeric carbon is the carbon that was already containing the aldehyde or the ketone functional group. We can have two main forms of that cyclized form. You can have one in with the OH at the top and one which is at the down. Now we call those two enantiomers, or those two stereoisomers are anomers. So they are anomers because they differ in the configuration around the anomeric carbon. This interconversion of the alpha and the beta form, or the interconversion of the two anisomeric stereoisomeric form of the anomers, is what we call meta rotation, and this one normally occurs in a solution, mostly aqueous solution. So let's have an example for the formation of this compound, which is a cyclic form of the sugar. We have a six-membered pyranose. We have a ketose with OH on carbon 6. So with this one, the reaction is between the carbon 2 and the OH on carbon 5 seen here. So for us to form a cyclide form of this sugar, this is a fructose, the reaction is between this ketone and this OH. So between carbon 2 and carbon 5. So the six-membered furanose is the reaction of carbon 2 and carbon 5. Then the 5-membered is between carbon 2 and carbon 5. Then the 6-membered furanose is between carbon 2 and carbon OH or carbon. So take note, for us to react this one to form the sugar, the OH on carbon, or the O on the carbon 2 picks the H on the OH of the carbon 5. Then the O on carbon 6 bonds to the carbon of carbon 2. So we get a cyclized form of the sugar. So this is a cyclized form of the sugar. In here, this is carbon 1. This carbon 1 is this one. This carbon 2 is this. So this O is basically this one. Then we have 3, 4, 5, and carbon 6. Carbon 6 does not form part of the ring system. This is an anomeric form that forms a furan. So if a sugar, this one is what we call the Fischer projection form, cyclized to form the Howard projection, the name becomes fructofuranose, or let's say furanose. So here's a fructose which is made of, or the furanose which is made of 5-membered ring with 1 oxygen. So it is alpha D. The alpha comes from the fact that the OH on the anomeric carbon, which is the carbon 2 here, is down. Then here we have beta, which shows that the OH on the anomeric carbon is at the top. So for fructose, fructose forms what we call furanose, because it's 5-membered ring with 1 oxygen. Then glucose forms what we call a pyranose, because it's a 6-membered ring with 1 oxygen. So let's continue with the oxidation reduction reactions of monosaccharides. So monosaccharide can be oxidized or reduced in a chemical reaction. If you have a glucose molecule, it can have an oxidation on carbon 1, on carbon 6, or simultaneous oxidation carbon 1 and carbon 6. If aldoses are oxidized carbon 1, we form what we call aldonic acid. So specifically, we have glucose undergoing oxidation, we are going to form gluconic acid. If they are oxidized carbon 6, we form what we call an aldonic acid or uronic acid. So glucose becomes gluconic acid. If the oxidation occurs at both carbon 1 and carbon 6, then this dicarboxylic acid is called an aldaric acid. So glucose becomes glucaric acid. So if you have a strong oxidizing agent like nitric acid, that can form an aldaric acid. If you just use a mere oxygen, you are going to just oxidize carbon 6 as an OH to form the gluconic acid. Then if it is just a bromine water, you are going to have oxidation of carbon 1 to form what we call the gluconic acid. So basically, reducing sugars are the sugars that free anomeric carbon or free hydroxy group on the anomeric carbon to undergo oxidation. So if you add, this one is what we call a Benedict test, which is made of copper 2 plus ion, an oxidizing agent. So if you add this one to this sugar, there's going to be an oxidation of the sugar to form an oxidized form. So this one is an example of gluconic acid. gluconic acid. So for the test, this provides a very good test for the presence of glucose in the urine. So it is a chemical test which you get a red precipitate. So basically, the copper 2 plus is blue colored. When it undergoes oxidation, it gets reduced to copper 1 plus in the cuprous oxide. So this oxide is having a red color, which is copper 1 plus. Here is copper 2 plus having a blue color. This is what is used in the test of excess glucose in the urine. Other tests, this one is called the Benedict test. Benedict test. Other tests include that of a Tolling's test and Ferrin's test solution. Ketones are not easily to be oxidized because ketones OH or the OH on the carbon 2 does not undergo oxidation, but rather they can undergo what they call an any-diol reaction, which is an isomerization reaction. When you treat, let's say, an aldehyde containing group with a base like sodium hydroxide, which is called an alkali, it is going to form what you call an any-diol. Then further oxidation will form a ketone, which is like this. So conversion of glucose to fructose is through an any-diol reaction, which produces the any-diol intermediate through enolization to produce what we call glucose. In the same way, glucose can be reduced, or aldehydes or monosaccharides can be reduced if you use a reducing agent like sodium borohydride or let's say hydrogen. So here, if you have a glucose and you reduce the hydroxy group or let's say the aldehyde group to OH, we form what we call a glucitol. In general sense, if all aldoses are reduced to form what we call an alditol. So glucose becomes glucitol, fructose becomes fructitol. If you have ribose, it becomes ribitol, and all